Okay, we'll start from here. Mostly, again, we'll be going through the notebook rather than text. But if you have any questions from the text, please raise your questions. And we'll be happy to discuss that. Okay, so this is a pretty straightforward cube function, x to the power of 3. And the most important thing is basically we want to see from this section is how TensorFlow functions are working, and how TensorFlow graphs work, and the tracing, how the tracing works. Now, I think Jerome mentions basically TensorFlow 1, you almost always have to deal with graphs when you build models, but now in TensorFlow 2, you don't have to. You can just use the eager functions or eager executions without using the graphs to build your models. And but in TensorFlow 2, they're still here, but they're much simpler to use. Now, I'm curious to see or to ask if it's completely avoidable to not use TensorFlow graphs in TensorFlow 2. So please chip in if you have some experience with that, and or you've been basically, we've been basically using just tf.keras. It seems like it can handle most of the cases, but I guess he does want to demonstrate that there are some use cases that we still need TensorFlow graphs. So anyone has any thoughts or comments on that? Whether or not to use graphs or not, to use graphs. Okay. Does anyone have any experience with TensorFlow 1? And how much of a change you're seeing compared to TensorFlow 2? I know I had some experiments with TensorFlow 1. You always have to, call tf.placeholder and tf.session and to build the graphs before you can run models. And so it was quite complicated compared to TF2 relatively. Anyone has any thoughts? No? Okay. All right, so let's keep going then. I think this is pretty straightforward. It's just basically using TF cube, which is defined here, and TF function cube. And then you passing another 2, which means this 2 is passed into cube function. Then you get 8. So, and if you pass in the float, then you get a 8.0. So you could use decorators at tf.func, and as he said here, it will analyze the computations performed by the cube function and generated an equivalent computation graph. So whenever you call this tf.function, basically it will TensorFlow would generate a computation graph for you. And so it's pretty handy. And also you can still call your original Python function by just doing .python function here. Okay. And as I mentioned, I was talking about, eager execution or not. And eager execution is basically you don't create a graph and you just execute it immediately. And you can specify the parameter in some of the functions as run eagerly equals to true. And that function will be executed immediately. So, okay. Any questions, any comments up to this point? No? Everyone has been quiet?
Seems a bit straightforward. So
okay.
Let's just continue.
Cool. Okay. So he does adding some new codes, and actually a lot of new codes that's not covered in the text. So we'll go through these codes. Okay. And there's something that's called, there's a method that's called get concrete function. And it's basically a way to have an eagerly executing wrapper around the tf.graph. So basically, your tf.graph becomes eagerly executed, meaning immediately executed. And every time a function is traced, a new concrete function is created. You can directly obtain a concrete function by using get concrete function syntax. And yeah, so, and as he called it here, basically tf cube dot get concrete function and pass into a variable called concrete function here. And you get an eagerly execute a wrapper out of that. Okay. Any questions on that? Okay.
So what is the advantage of that versus the other graph? Is there something mentioned in the code?
I don't think it's mentioned in the codes. Let me just see if there is concrete. No. I don't think it's mentioned here, but I think the main difference is it allows you to eagerly execute it instead of basically going with the graph calculation.
So does that mean like you won't run through like the graph mode? Is that what eagerly executed means here? I don't understand what eagerly executed means.
Yeah, eager execution is basically just you immediately execute something. Yeah.
Okay.
Yeah.
Without building graphs. Eagerly, so it won't build graphs. And this is according to Google's TensorFlow guide. TensorFlow's eager execution is an imperative programming environment that evaluates operations immediately without building graphs. Operations return concrete values instead of constructing a computational graph to run later.
I see. Okay.
Mm-hmm.
I think a graph is like a container for a calculation. You design the calculation, you encode it in a graph, and then it can be reused. You know, when you need it, you can supply it with the values and have it execute. But otherwise, you can save it for later to include in your models. I'm not really an expert on this, but that's what I understand.
That makes sense. But how is then a graph different definitionally from a function?
I'm about to go through that right now. What is graphs? What are graphs?
Yep.
Jump
in.
And so, yeah. So this was taken from TensorFlow tutorial, and in the previous 3 guides, and obviously I'm not showing that, you have seen TensorFlow running eagerly. This means TensorFlow operations are executed by Python operation by operation and returning results back to Python. Eager TensorFlow takes advantage of GPUs, allowing you to place variables, tensors, and even operations on GPUs and TPUs. It's also easy to debug. So graphs are not as easy to debug. For some users, you may never need or want to leave Python. However, running TensorFlow op by op in Python prevents a host of accelerations otherwise available. If you can extract tensor computations from Python, you can make them into a graph. Graphs are data structures. So in this context, graphs are data structures, okay, that contain a set of tf.operation objects, which represent units of computation, and tf.tensor objects, which represent the units of data that flow between operations. They're defining the tf.graph context. Since these graphs are data structures, they can be saved, run, and restored all without the original Python code. So, and this is what a graph structure, 2-layer graph looks like in TensorBoard. And identity, ReLU 1, add operation, and matrix multiplication plus ReLU. Then you add operation and matrix multiplication. So that's kind of a 2-layer graph. And I think the main benefit is it can be saved, run, and restored without the original Python code. And it is supposed to be faster than your original Python code eagerly executed. Okay, and again, TF1 is mainly depends on graph structures rather than eager executions.
So we just said that eagerly executed means no graph, right?
Mm-hmm.
But we are saying that the graph makes it run faster?
Graphs, yeah.
Huh. Okay.
Yeah. So, and it says running TensorFlow op by op in Python, meaning operation by operation by Python, prevents a host of accelerations otherwise available. So it prevents a host of accelerations when you do eager execution operation by operation in Python. Now, how exactly does the graph accelerate the operations? I'm not sure. Okay, and
I can add something which may not be relevant. However, I think these graphs coming maybe 8-10 years back, when they may be competing with the Spark guys, where they used to have like it's called a lazy execution. So what you do is like you don't define, you don't execute it. All you do is you have a number of operations. Let's say you have 100 operations, and you just define the graph for it. So those not get executed. At the time of execution, the TensorFlow or a system will find the most optimal path of executing those operations. So perhaps you're doing 100 operations. It finds a way that, oh, I don't need to execute these 100 sequence of steps. I perhaps need just 20 steps out of these hundreds. So that's like most optimal way of running it. So I'm just guessing it. And that's how the Spark, they used to do it. Like they used to call it a lazy execution. So I guess these like TensorFlow 1.0 was the lazy execution, where they are not executing all the operations, just building those graphs. And when you call the method to execute, they find the most optimal track or a solution or a number of operations, and then return back the value for you. And then perhaps that's what they are calling it's the faster.
Yeah, and actually pulled some paragraphs from TensorFlow tutorial as well. So, and then let's read through that. With a graph, you have a great deal of flexibility. You can use your TensorFlow graph in environments that don't have a Python interpreter, like mobile applications, embedded devices, and backend servers. TensorFlow uses graphs as the format for saved models when I export them from Python. So TensorFlow does, I guess, use graphs as the format for the models saved and deployed, I guess. So that you can use in different application environments. And graphs are also easily optimized, allowing the compiler to do transformations like statically infer the value of tensors by folding constant nodes in your computation, separates subparts of computation that are independent and split them between threads or devices. Simply arithmetic operations by eliminating common sub-expressions. There's an entire optimization system, grappler, to perform this and other speed-ups. In short, graphs are extremely useful. Let your TensorFlow run fast, run in parallel, run efficiently on multiple devices. However, you still want to define our machine learning models in Python for convenience and then automatically construct graphs when you need them. Is that clear? Okay, so that explains a little bit of how graphs, why graphs are faster, and how TensorFlow adopts graphs in different environments. I guess it's just a more efficient data structure. It seems like for production environment.
However, in TensorFlow 2.0, they kind of like go away from this method of graphs, like that eager execution, that you don't need a graph, you just run those operations straight away. And I think that's the competition with the PyTorch, because PyTorch doesn't have a concept of graphs whatsoever. So this method, which the graph method, is sort of like outdated, I guess. I'm assuming that's why they have TensorFlow 2.0, that eager mode introduced.
Yep, absolutely. And let's, I did find this, I thought it's probably good to go through this as well. Effective TensorFlow 2.0 best practices and what's changed. And it's dated as of February 2019, so perhaps that was the time. And I think, if I remember correctly, that was close to the time when TensorFlow 2.0 was released. And this article has a brief summary of major changes. API cleanup, obviously we've seen that, and incorporates TF to Keras. Okay, and pretty much and many APIs are either gone or moved in TF 2.0 versus TF 1.0. And they have simply been replaced by tf.summary, tf.keras.metrics, tf.keras.optimizers, and so on. And yeah, so many of the previous 1.0 APIs were gone, and they were cleaned up. And here's the eager execution. TF 1.x requires users to manually stitch together an abstract syntax tree, the graph, by making tf.something API calls. It then requires users to manually compile the abstract syntax tree by passing a set of output tensors and input tensors to a session.run. I remember I always have to call this when I deal with TF1. By contrast, TensorFlow 2.0 executes eagerly, okay, like Python normally does, and in 2.0, graphs and sessions should feel like implementation details, okay? And no more globals, okay? TF 1.0, 1.x rely heavily upon implicitly global namespaces. When you call tf.variable, it will be put into the default graph. So even by calling this, will be put into the default graph. It will remain there, even if you lost track of the Python variable pointing to it. You could then recover it. But in TF 2.0, it eliminates all of these mechanisms in favor of the default mechanism. Keep track, meaning keep track of your variables. If you lose track of a tf.variable, it will just get garbage collected. So you need to keep track of that by yourself. TensorFlow won't track it for you in the graph. Again, graph stores, right, saves these things for you, but not in TF 2.0 unless you call tf.function, okay, which is this, to have the graph computation. A session.run call is almost like a function call. You specify the inputs and the function to be called, and you get back a set of outputs. In TensorFlow 2.0, you can decorate a Python function using tf.function, which is what we see or saw right here. So that's the decorator, right? So and this mechanism allows TF2 to gain all of the benefits of graph mode. Performance, so meaning this allows you to gain the benefits of graph mode. Performance, this function can be optimized, no pruning, kernel fusion, portability, can be exported, re-imported, allowing users to reuse and share TensorFlow functions. So now you can kind of interchange Python code and TensorFlow code, or eager execution versus graph execution, with tf.function, or run eagerly equals to true. These parameters help you to kind of, or decorators help you to kind of interchange these two modes in TF2 now. Okay, and let's see if we need to, yeah, we'll go through these probably in a little bit. Any questions or comments on this? Is that clear? I thought this was a good brief summary of major changes and serves a background of why we were doing this. Okay. And you can call .graph. So we had the variable named concrete function, right? tf.get concrete function, tf_cube.get concrete function. That's the concrete function variable defined here, and we can call .graph. Then it gives a function graph object, and we can call the method of that .get operations, and that gives us kind of a list of the operations in that graph. Okay, and you can get operation by name, which is X. So then you'll get this operation, and get tensor by name. And you can get the signature. And signature would include the inputs name, type, and output name and type. That's what the signature is. Okay. Tracing and performance, TensorFlow tracing, and how TF functions trace Python functions to extract their computation graphs. So when you actually do some computation in graphs, structures or graph computations also trace whatever you do. And let's see how it traces it. So again, that decorator tf.function, pass that into a result variable tf cube with tf.constant 2.0. And it basically says new shape trace, and no trace. So these two ones would be traced, but somehow this one is not traced. Okay. And this has a warning. 5 out of the last 5 calls triggered tf.function retracing. Tracing is expensive, and the excessive number of tracings could be due to creating tf.function repeatedly in a loop, passing tensors with the different shapes, passing Python objects instead of tensors. And tracing costs some overheads. Okay, this again is from TensorFlow tutorial. What tracing is. Although tracing small functions is quick, large models can take noticeable wall clock time to trace. This investment is usually quickly paid back with a performance boost, but it's important to be aware that the first epochs of any large model training can be slower due to tracing. No matter how large your model is, you want to avoid tracing frequently. And you can add an eager-only side effect, such as printing Python argument, so you can see when the function is being traced. So, and I think there was another example from here. Tracing graphs. Right here. So I think basically, in a nutshell, tracing helps your functions to run faster if your models, if the models are pretty large, but the first couple epochs will be slower. And but in the end, you get a performance boost as a payback. And you can specify, this is very interesting, you can specify the arguments passing into the decorator for input signature. And it basically, input signature just optionally provided to tf.function, and it specifies the shape and type of each tensor arguments. So basically, you're specifying the shape here and type here. So now, whatever is input into this function needs to follow this shape and type. And if you don't follow that, it'll give you an error. And so, and if we, if we change this to, so this still follows this shape, right? But if we change it to, let's say, 25 to 25, so 125, 25, so give me an error. It will say value error, Python inputs incompatible with input signature. Okay, because it doesn't follow that shape requirement. Okay, so change it back. And again, I think he was doing the same thing. Basically, Python inputs incompatible with input signature, this requires to be 100, none 2828. Okay, and I suppose if you don't input tf.float 32, it will also give you an error. Any questions so far? This was not covered in the text.
So does it mean like when you run that first shrink, it takes longer than the second shrink, right? And that's kind of the advantage. Is that what tracing kind of in a nutshell is?
Yes, I believe that's what it is.
Okay.
Yeah. And in the first couple runs, yeah.
Okay, so it's practically if you were running, yeah, that's running through a couple of, epochs, you'd see, okay, the first few will take a while because of the tracing, and then it should overall be faster because kind of has computed this one. Okay.
Yeah, that's right. So let's see if this mentioned tracing.
So if you basically squeeze in a time function somewhere in between those two processed images, would we see a benefit? Yeah, let me check if there is.
Yeah, so let me see if tracing. Yeah, this tutorial also provided another example of tracing. And right here. And it says it's basically x times x plus tf.constant 2, and passing in the decorator. And this is traced the first time. The second time through, you won't see the side effect. So this was what we were talking about. This traces each time the Python argument changes, as a Python argument could be an epoch count or other hyperparameter. So I think this is but you want to avoid tracing frequently. That's what it is, as it says right here. And oftentimes, and if you're getting unusually poor performance, it's probably you're retracing accidentally, meaning you're tracing repetitively.
So what is the last comment before the prints? It says this retraces each time the Python argument changes. Could be an epoch count or other hyperparameter. So nothing has changed in this case though, right?
Right. Meaning
oh,
like,
no, actually, okay. It became from TF constant, it became a number. Okay.
Yeah, that's right.
Okay.
Yeah. So that changed. So meaning if an epoch counts changes, meaning you're running through a different epoch now, then it retraces.
I see. Okay.
Yeah. Okay. And you can revert back to eager execution. Okay. So let's say you don't want the graph execution anymore. You can just revert it back to like using set, you can do call models and layers directly as callables, or you could do model.compile run eagerly equals to true as a parameter, or you could set global execution modes via that So that will just set the global execution mode to be eager execution. Okay. And right here, so that's how you use it, model.compile. This is your model right here. Okay. And you can just specify that parameter.
So in theory, if you do use tracing while training, it shouldn't trace frequently, right? Because nothing will be changing from epoch to epoch. Does that make sense? Or am I missing something?
I think for the first couple
Correct.
epochs, yeah.
Right. But after that, nothing should change, right? So why does it say that? I mean, why switch back to ego mode? I'm just not understanding that part.
I think you might, so this is the reason. You might find yourself seeing long stack traces.
Right, yeah, so why would that happen?
So in the situations where graph makes debugging tricky, so when you're debugging, it's easier to use just, look at the eager execution. Yeah, and stacking traces should be relatively short and easy to comprehend. So that's that.
Cool.
Debugging is made easier when you do that. Yeah.
Rakil, why do you say nothing will change? Like, will the learning rate not change if you use a scheduler?
That's a good point. Yeah, I'm saying so. Yeah, that's a good point. Yeah. So if you don't change that, then in theory nothing would change, right? Like, or is there something else? Yeah, that's a good point. Like learning rate is something, if you're having a scheduler, will change. So that should call the. Oh no, actually that will not, right? Even though if the learning rate changes, it's the type or the shape that hasn't changed. So it shouldn't affect, right? Even though the constant learning rate has changed. That's what I think Wenchang shows in that, the last example that you pulled up, Wenchang, on that page.
This one?
To the bottom where you were showing tracing.
This one?
Yeah, right, this one. So when the shape and the type didn't change, tf.constant2 we passed in, and then we passed in tf.constant3, you see that in the output, tracing was only printed on the first one, and the second one tracing is not printed, right? So that in effect reflects how learning rate would have changed, but doesn't call tracing.
So tracing is, so the point is that tracing only causes changes if shape or type change.
Yeah, that's what looks like, yeah. And that's why you see that when that 2 or 3 again got called later, but they were not tf.constants, you can see tracing gets printed again. But I wonder why did tracing get printed when we passed 3 in, the last 3?
It's perhaps because you're not specifying with TF, TensorFlow types.
I see, okay. Yeah, could be that, okay.
Yeah.
I'm surprised nothing is written in the book about this, and yeah, this web, yeah, you need to look at this page.
Yeah, and because then you might, and TensorFlow might understand it as, okay, this might be epoch count, because I assume you don't pass epoch count into tf.constant or tf.variable.
Cool, okay.
Yeah. Yep.
So have we understood why on that example, the third, so it feeds in different constants into the TF cube function, and tracing is called when the first time the shape changes, it's called the second time the shape changes, but the third time the shape changes, it's not called. Does anybody understand that?
Which page are you talking about, Joseph?
This is in the notebook, in the notebook, and it's right under the section how TF functions trace Python functions to extract their computation graphs. It's
Yeah,
like
I didn't
two or three cells
understand
under that.
why this is not traced.
Actually, I get a different result. When I printed that out, I got that error or that warning the moment I printed the second one out.
But this was these two were traced because of new shapes, but somehow this was not traced.
My understanding was that there was a repetitive call to that function. So that's why it's saying that you're calling it too many times, hence I'm not tracing. If you switch that order around, if you put that last result, which the shape 2 by 3 above the one with the 2 by 2, I'm guessing that it will complain for the 2 by 2 one because you're going to call it more frequent. That's what my understanding with that tracing was.
Okay.
Does that kind of make sense, Joseph? I'm not sure. This is my guess, though.
Well, we can try that.
Yeah,
it's kind of. It seems like that's. It seems like that's what it's doing, but it seems kind of arbitrary to me. Like, and where would you set the number of repetitions that it would, that would trigger on? I mean,
I think the key that he's trying to show here is that you don't want to be passing things in with changing shapes or changing types when you're tracing. Kind of, that's what I got in essence from this. And so if you think about it in a practical stance, when you're trying to train a model, like Srinivas was saying, LR would change, but the type of LR or the shape of LR wouldn't change. So you'd still get the benefits after maybe a slowdown in the first few epochs, but after that, it should be faster. I don't understand why this is not like a default setting and why this is something we need to do. That is something which I don't understand.
Yeah.
So yes, this does get traced. 3.2 right here. I just changed. Yeah. So if let's say I add in.
So it's because of the frequent calls that it's not getting traced, or?
Yeah, I think that's what it is.
Okay.
Oh, it still gets traced.
Yeah, I don't know what
Is tracing something that's used to optimize the because you have built a graph and the graph depends on the shape and the type, and if you then go trace while changing that, then you can't optimize because now your optimization again has to change.
Right. So actually, if you look at that 12.4 figure, I think that's what I also understood from that figure in the book.
Yeah.
This one?
You create that graph mode, right? And then if anything sits in that, it can reuse that graph. Whereas if you change the shape or the type, then I guess you need to recreate this. So that's what is getting retraced over there.
Yeah, because you have to throw out the traces you have, or tracing is something that how to move through the graph, quote unquote, or approximately that, and then you have to rebuild the graph. So you have to, that's where then the tracing is no longer useful.
Is anyone else more familiar with this? I'm just saying things as we read along. And
yeah, it looks like you'll need to go through it in more detail to figure out all the nuances. And to your question, Rekil, though, in eager, none of this matters, right? So invariably, if you're executing, then you don't need to really do this. It's only when you use functions and are trying to build a graph and trace, which in the TF2 eager execution default mode you never do.
So does that mean that that default mode is always going to be faster than this mode?
Not necessarily, because the way and again, as you said, if somebody is much more familiar, because this request seems like it requires a lot of digging to figure out the details, but my guess is the TensorFlow to PyTorch competition, it was also the usage thing of just defining some without creating the graph and then running the session. It was just that Python used Python's imperative execution to just handle everything eagerly. To handle everything, I mean, they didn't call it eager, they just executed it this imperatively as Python did. Now, my understanding is that because of that, if you just used TF1 though, that you would still, because you manually built the graph and stuff, you'd probably be faster. But faster didn't matter because productivity of the developers is much more important than, when your speed of hardware is changing much quicker, then you optimize for the bottleneck, which is developer productivity. So that's why PyTorch began to take off, and then TensorFlow had to react by throwing away all this non-eager stuff and just go eager as default. So I'm not sure that eager therefore would be faster. It's probably faster to build a graph and then do it. But the problem is developer productivity.
Okay, I see. So, I mean, I think just in like normal workflow for someone, you'd probably start with eager mode. And then if you want, I don't know if this would help, like probably at production time when you're trying to move something across.
And yeah.
Okay.
Yeah, that makes sense. Yeah, eager mode would definitely, make debugging easier. Cool. So let's keep going. And also there's something that's called tf.autograph. When you have flow and loops in your function, and you call it the decorator tf.function, these control flow statements get converted into by tf.autograph. So it kind of, by its name, automatically graph your control flow statements. And this is because, as Jeroen says right here, Python does not provide any other way to capture control flow statements. It offers magic methods like add, multiplication to capture operators like plus and multiplication sign, but there are no while or if magic methods. So it uses something that's called tf.autograph to convert the control flow statement like for loop. And while loops like this. You could use tf.while loop as well. And in the end, I think it demonstrated a way to, one second, this one, there was an example that demonstrated after the conversion, what does the code look like? One second, right here. So this was a function with if statements, and when this is converted by tf.autograph by default, it will look like this. So your my function with if else would become something like this, and you can read it by tf.autograph.toCode. So it'll become a function, and it's not as readable, but it automatically converts like if else statements and loops, prig, return, continue to something like this.
So I think that to answer Masha's earlier question is that what's the difference between a function and a graph? I think a graph, I believe that a computation graph is the equivalent of a function that's been translated into TensorFlow, so that it's basically, it operates the same as a function does in Python, but within TensorFlow. So you create some specification or signature of a calculation, and all you have to do when you finish, okay, and then this tracing process is what happens to produce the final computation graph. And then once you have a final computation graph, all you need to do is supply it with the inputs, and then it can do the calculation in I guess it would go to eager mode.
Yeah, that's exactly how I intuitively reason it.
Yeah, and look at the if. So if statements and else statements. So if becomes its own function right here. If body, try do return equals to true. And so I think the multiply becomes this argument LDX times argument LDX. Else except do return equals to false. And else body becomes the else statement becomes else body. Then try this x minus 1, return x minus 1, except do return equals to false. So it's not it's pretty much not as readable, obviously, but it seems to separate, each statement into functions and set a state to it. Okay. And this becomes a TensorFlow operations. Okay. And it says, most of the time, autograph will work without special considerations. However, there are some caveats. Okay. And also this demonstrates the speed up. Okay. This is a sequential model. And you have an eager time. And you have the graph time. Timed it using these two lines of code. And the eager time is 5.3 seconds, graph time is 2.36. So I think Srinivas, is probably right. Like when you're done with dev mode, you probably want to convert something into graph. Convert your model into graph using graph computation.
Which in essence looks like just that last but third line, right? Just to wrap it up in tf.function, and seems like that's pretty much it.
Yeah, that's pretty much it.
That's cool.
Or just decorator, right? It's the same thing as decorator. Yep. And so now you have an eager model by just calling this, or a graph model by wrap it around with a tf.function. Then it's a graph-based model. So, and I think number is the iteration number, probably. Yeah.
Yeah, the just averages.
Yeah. Okay, and you can see it almost it's you speed up 100%. Well, yeah, 100%. Right? What? Yeah, you reduce your execution time from eager by more than 50%. So more than 50%. That's pretty big deal.
Can you jump back to the PDF? I have a question there, Wenchang.
PDF, this one?
Yes, yes. Right above the autograph and tracing section. So yeah, just scroll up slightly. There's a warning. Yeah. And if you read that, it says, so yeah, the last, yeah, go ahead.
Yeah, if you call a TF function many times with different numerical Python values, then many graphs will be generated, slowing down your program and using up a lot of RAM. You must delete the TF function to release it. Python values should be reversed for arguments that will have few unique values, such as hyperparameters like the number of neurons per layers. This allows TensorFlow to better optimize each variant of your model. This is interesting because we did not do that, I assume.
Yeah, we don't know how to release it. Yeah, that's one thing. The other key thing that I wanted to kind of, I just dawned on me now is that when you use tf.constant, then like we discussed, I think if that shape and type has already been used, then you'll reuse that graph. But whereas if it's a Python value, that is like how we were passing in 2 and 3, looks like that is going to always call and create a graph. Right? That's what it means, right? Because it says many times the different numerical Python values, then many graphs will be generated.
Yeah.
And that's why I think in the intro to graph TensorFlow docs that you were showing, that last call also had like tracing being printed out because it was a Python value that we were printing.
In fact, Rekal, the paragraph above where Wenchang has it on the PDF, if you stick with it, he tells you that if you call functions with varying number or somewhere right there, I saw that, then it'll create one for every new Python value, create a new graph.
That's what I don't think it's for a Python value, right? Python value, like irrespective of if it's the same shape or size, you will create one more. Whereas if it's a TensorFlow constant, then if it's the same shape and same type, then you reuse.
Yes, that's what
right.
I meant.
Okay.
That,
yeah. Okay. Yeah. Okay.
That different numerical Python values, then it will create a graph for every value.
Correct.
Every
right,
Python value.
Python value. Right. Okay.
So you'll have multitude of graphs for each value will have its own graph.
Right. Okay.
But the warning says you're going to use up a lot of RAM. Now, these graphs, once constructed, they're not run, they're not compiled in TensorFlow. They're just constructed, the architecture is designed, and it's built that way, right?
Yes, and stored in memory though.
And stored
each data, remember what Venkat also said, these are structured, the graph is a data structure. So you build the data structure, store it. You build the data structure, store it. You build it, and you'll exhaust your memory just building data structures for every value of your Python variable. You're rebuilding a graph, which is a data structure with that Python value.
Yep.
Until you garbage collect, if you're no longer using it. That's the release thing he's talking about. But as Rekal said, I don't know whether, how you release it, whether you can actively release it or you wait until all references are removed, at which case it will be garbage collected.
Right. And I guess, I mean, one way of doing that is just delete,
Yeah, delete or just equate it to none, I guess. And then if you garbage collect forcefully, that should clear it.
Yeah. It's just, when do you do that? I guess that's the
that's
question.
A good point.
Yeah.
Especially when you're training, like where do you squeeze this in between? Like if you're running 100 epochs. Yeah, that's the part I still don't get. But this is cool that can make it really half the time that took, right? From 5.3 to 2.5 seconds.
Half of the time is significant. More than half the time, 60-70% reduction on time. So, and by simply doing tf.function, so then it becomes a graph model. So I guess, before you deploy, you just do that.
I think it is also to look out that you can change always your Python values to TF tensor or something like that. Because if you see the example of TF-Cube10 and TF-Cube20, you have the same example above with TF constant 20. So if you look carefully, you can avoid the generation of the two graphs if you pass Python values instead of tensors.
Yeah. So if you pass, it's always a new graph for every numeric distinct value. Yeah.
But if you use TF constant, you can avoid that. So
Yeah.
so maybe look out for Python values, pass it to TensorFlow
Yeah.
methods.
Yeah, and this is why this was a new retraced, right? So because it's a numerical value, but this is not.
Python
right?
numerical value.
Yeah, this is not. This is retraced, but this one is not, because this one is using tf.constant. Yeah, explained right here. So okay, anyone else? Okay, let's keep going. And this is interesting, right? It also records, all the operations for you, right? So if you have a for loop of 10 loops, right, then it records all the operations for you, and you can extract them in a list by calling .get operations. Right. So, but you have to use get concrete function first. And you can use a dynamic loop by using tf.while loop, which is here. And also you can get that operation from here by calling .get operations. So
sorry, Venchai, I have a question actually. So that means when we're training now, and let's say we're training for like 100 epochs, talking to what David was saying, is we're going to end up creating 100 graphs, right? Because epoch is not going to be passed in as a tf.constant.
Yeah.
And so we'll end up with like 100 graphs.
At least retraced 100 times.
Right,
traced
yeah,
100 times. Yeah.
Traced 100 times, right?
Yeah. And you will have a stack of graphs. And this is why debugging becomes very hard.
So then practically, how would one go about using this? Like, you can't run it for like just 3 epochs, right? Or a fewer number of epochs.
Right.
Yeah,
right. And I think, but you're saying because every time it's traced by passing a numerical value per epoch, and
right. Or the learning rate, actually, for what Srinivas was saying, even for the learning rate, since that will be a Python value, it will change, right? I don't understand now. I kind of.
Yeah, I don't know how this is faster with a bunch of epochs.
Right. Okay.
But here it is. No matter how large your model, you want to avoid tracing frequently.
Yeah, but how do you avoid tracing frequently? Like if you're running for 100 epochs and there is a learning rate which changes or the epoch which changes, right? How do you control that part of it?
Yeah. Yeah. Input specifications. Tensor arguments to avoid retracing. So this, let's say, better performance. I think it's probably from here. If you avoid, let's say, avoid tracing. No.
Are we sure that it has to trace with when you change the learning rate? Because I thought that wouldn't. I mean, it seems to me, or my impression is that the graph, the structure of the graph has nothing to do with the individual tensors that you use for inputs. They exist independently, and that's the whole point
that
of
is,
making a...
That is correct. If it's a tensor though, right? But the learning rate is not going to be a tensor that will be passed in, right? We usually pass it in like a Python value, right? If like what you're saying, if it was wrapped in like a tf.constant, then yes, you shouldn't be retracing that at all. But from the warning note, it says if Python values are passed in, which is like 2, 3, 4, that's how I would imagine our learning rates would look like, then it gets retraced.
But having said what I said, because the learning rate changes, but you pass in a single value and then everything is changed within though, right? So you don't pass it in again and again.
I mean, then let's jump back to the epoch question, right? The epoch changes though, right?
The epoch does change. And that's where I was wondering, is the epoch going to be passed in as a TensorFlow variable or a TensorFlow entity then?
Right, at least I've never seen it being passed like that. So that's why I'm very curious how you would avoid retracing.
Yeah, that's where this whole tracing thing requires deeper dive.
There's a couple ways to control the so let me just read this. Retracing helps ensure the TensorFlow generates correct graphs for each set of inputs. And I mean, just by reading this, we probably need a different graph for each set of inputs. However, tracing is an expensive operation. If your function retraces a new graph for every call, you'll find your code executes more slowly. To control that, you specify input signature to limit tracing. So I guess we specified an integer, so this should fail. So meaning you could allow what to be traced and what not to be traced by specifying, a certain set of
signature parameters.
Yeah.
Okay.
Yeah, that makes sense because the graph is really independent of the inputs, the numbers that you want to it to crunch, right? So as long as it knows what the inputs should look like, it doesn't care what the specific inputs are, or it shouldn't.
And you can specify a non-dimension to allow for flexibility in trace reuse, and also cast Python arguments to tensors to avoid retracing. I think we were talking about that, right?
Right.
So
yeah.
You could do this or just do that number of steps.
Right. Okay. So that makes sense. You're passing it in as a TF concept. Okay.
Yeah. If you need to force retracing, create a new function, separate function objects, and guarantee not to share traces. The separate functions objects are not a guarantee not to share traces. Okay. This is a complex topic, I guess. Yeah.
But it seems like these graphs have to do with this modular structure of when you build neural networks layer by layer. It seems like a computation graph. I mean, I haven't made the connection yet, but it seems to me like a computation graph is one of these Lego pieces that you use to build your model, and then the model exists independently of all the inputs, and then you give it the inputs, and it just crunches through all the computation graphs.
Yeah, the graph is there more, at least as I understood in using TensorFlow 1, is to enable you to go do this auto diff part of it, because that's once you build the graph, you know the connectivity of the nodes, and then you can trace back and forward. So
yeah, so I think that when you're building models, correct me if I'm wrong, but I think if you're building models with the simpler interfaces, what do they call the sequential interface, or the sequential API, or I forget what the other one is. I think you're implicitly using function. I think you're implicitly using these computation graphs. You just don't see it. It's all under the hood.
Oh yeah, that's what PyTorch does, because that's the thing I was saying about developer productivity. Because when you had to define the graph and run the sessions, you were interacting directly with setting up the graph and running the sessions and all of that stuff. And PyTorch just abstracted it all away and said it's as easy as programming in Python. And then TensorFlow guys had to catch up to say,
competition
we can be simple too. But when you're simple,
competition is great.
Right. But when you're simple, you are not as fast, though.
But I think that the speed comes from when you have to build something like a ResNet where you have repeated units of the same type, right? So you can imagine that building these computation graphs as Lego pieces and then putting them all together, they all share the same, you're building identical units, copies of identical units and putting them together like Lego pieces. I think that's where the speed comes from.
The speed comes from, I think, in the graph thing, you build it, and then you execute and you cache and you even the tracing part of it is you reuse. And that's, so the original way that TensorFlow did it, it didn't use kind of the Python imperative flow. So you execute as you go. You build statically, and then you kind of, as you said, feed in the data, and it automatically does the derivatives in the back. But PyTorch does it more, as I understand, not all great detail, but the fact is that it optimized for running it closer to the way Python runs its native code imperatively. So here, the point of what Weng Chang shared of eager to graph difference in speed is when you move to the eager mode, which improves developer productivity because you're not dealing with all these details, then you give up what you could have gained if you did the I guess what they call the TF function and the graph mode. So there is a trade-off involved. You could get better speed after you have done your model building and all that in a eager and debugged all that. Then you can put in the effort, as Rekel and Weng Chang were discussing, of to speed the whole thing up by getting into the graph models.
Yeah, and to Joseph's point, I don't think when you just subclassing from this, you're already using graph model, because then why would you use TF function here? Because this is just eager model. So previously, I think we were just running eager model and not graph model at all.
Correct.
And also,
I think under the hood, there should be a graph, right? Because when you save that model out, what gets saved at the end of the day is that graph data structure, right? So I don't know. I'm still not clear about that part, but that's what my understanding.
That is a good question, because yes, you're correct in that our data structure, whether it is the exact thing that tf.function of the eager model builds or a variant of it to allow it to execute eagerly, I don't know. That's what we'll have to look into the detail. You see what I'm saying? You're
Right.
correct in that a graph needs to exist, whether it's the same graph as what you get on tf.function and how that is utilized, I don't know.
And also the speed comes here. So for complicated computations, graphs can provide a significant speed up. If it's a simple function, it does not, okay? And this is because graphs reduce the Python to device communication and perform some speed ups. Now, also, if most of the computation was already happening on an accelerator, such as stacks of GPU heavy convolutions, the graph speed up won't be large. So these are important points to keep in mind. If it's a simple function, simple model, it might not. And if you're already on stacks of GPU, it might not either. So yeah.
It's interesting. He says simple model, and the example that they've given is a simple model, and you see like 50% gain. I mean, 100% gain over there.
I think the main thing is the one that says that it reduces the Python to device communication, because when you're running Python on like line by line, because it doesn't know, maybe it requests each line or something like that. No, it should request when it wants to print something to the console or something like that. But what I can say is that those graphs are, at least for TPU, PyTorch, are compiled. So each time that a graph is like get from the PyTorch code, it generates like an intermediate function for the TPU, that is the graph. So those graphs are compiled. So imagine each time it sees a new Python value, you will extract the graph and compile it. And you know that compiling in general is an expensive operation because it goes into the detail of doing optimizations and things like that on the graph, and then it outputs the code that the TPU need to run. But if your model, like think on an RNN or something that change a lot of the input shape, uh, it will need to create that graph for each thing. So on the TPUs, this kind of things are not optimal. The RNN, they have even a special RNN function, if I remember correctly, that you should call instead to construct it normally, because it will cause to reconstruct for each value of the RNN a graph. So that is why it says that graphs are bad if you do retracing, because at least for TPU, you get the graph and compile it, and that is the thing you send to compute, and this compute will only execute what is on the graph. So there is no more Python execution or things like that. That is why you get a speed up even on GPUs, because it compiles. I think it will like construct a well good kernel without Python interaction. So that is why it should run faster.
Awesome.
And yes, that is why if compiling and things like that were easy, then constructing each graph for different shapes should be no problem, but it needs to compile and optimize. So that is why doing that operation a lot of times will not be good.
Interesting. And I think Raquel, to your point, I think this is still a very complicated computations. I guess I misspoke a little bit. He was more referring to small functions.
I see. Okay.
Yeah.
Cool. Okay.
Yeah. But thank you, TYLC213, for explaining that as well. Very helpful. Appreciate it. I think it's probably a good time for us to stop, and the rest of it is it's also not covered by the text, but we're also on time is up. But I encourage everyone to obviously still go through that. This is similar to what we did before. And also he built customized optimizers himself, and by using tf.function right here, this is how you can use it actually, and incorporate that right here. Okay. So I would encourage everyone to go through that. And of course, we're going to go through the exercises, in the homework session. And perhaps, when we go through this chapter, we're still on chapter 11 for homework review sessions. But when we go through this chapter 12, perhaps I can add in the PyTorch stuff if we have time, because I do still want to do that. But, I don't want to take too much time from the main session anymore. So it's probably a good time to stop at the 5th session with this current chapter. And so on that note, does anyone want to say anything? Make a comment?
No, I just want to thank you for the great job you did taking us through this chapter. That was a lot of deep material.
Yeah, it was definitely a lot of stuff, and probably he probably should have explained a little more on some of the concepts, but fortunately we have TensorFlow tutorials to complement or supplement, and so that was helpful as well. Thank you, everyone.